Okay, now let's talk about changing the light frequency. Last time is about changing the intensity. Now is changing intensity is we change the number of photon. Okay, change the intensity means we change the number of photon. Means let's say the first one is we maybe change intensity. Is change number of photon. Maybe the first case is the light very dim light. That means it has very less photon, less amount of photon. And the second case we use more higher intensity. This one is sorry again. Yeah, this one has low intensity. High intensity means more photon. More photon. High intensity. Yeah, this is high intensity. Eject more electron lah. Eject more electron. High intensity, but still green light. Same type of light because we fix the frequency. But the second one, yeah, this is low intensity, high intensity, about the number of photons. Okay, it is about the number of photons. Now, if the second case is we fix the intensity, means the number of photons we fix. Okay, number of photons we fix, but we the number of photons we fix means the brightness. The brightness we fix. We fix the brightness. We fix the number of photons. Okay, but we change the frequency. We change the frequency. That means we change the type of light. This one is actually about the type of light we change. That means now I use the same intensity. Means the number of incident photon become the same. If incoming is a 4 photon, means the other frequency also has 4 photons. What I can say is like this. Maybe the first case I use the red light. Maybe the first case I use the first case I use the red light with only 4 photon. Okay, 4 photon. This one is at frequent. Okay, and then the second case I use blue light. I use blue light, a different type of light, but the intensity is the same. Intensity is the same. That means the number of photon is the same, but you have different frequency. Different frequency. We know that the wavelength of red light is we can say wavelength of red light is long, but frequency is very low. Frequency is very low, so very low energy. The energy for red light is very low. So the photon particle very small. But the blue light is a very long, very short wavelength. The blue one is very short wavelength, so has very high frequency. Very high frequency. So it has very high energy. It has very high energy. So we can imagine the photon is bigger. Photon is bigger because it carry more energy. Figuratively, I draw bigger, but it's not actually about the size. Yeah, it's not about the size. Size doesn't matter. It's about the energy, amount of energy it carry. Okay. So the number of photons still the same. You see, there are 4 photons. Here also there are 4 photons. The intensity is the same. So we can imagine the current will be constant. If intensity fixed, that means the number of electron ejected will be constant. So what I can say is the saturation current. The saturation current will be constant. Yeah, the saturation current will be constant. I just want to make this just green color. So the saturation current will be constant because the number of photon is the same. So they eject the same amount of electron. When eject same amount of electron means the saturation current will be the same, constant. But now you change the frequency, means you change the type of light. From maybe red light and blue light. We can imagine the number of photon is the same because we fix the intensity, but the amount of energy each photon carry is different. The red light carry less energy, the blue light carry more energy. because blue light has higher frequency. Okay? Okay. So, that's the thing. See? Changing the intensity, you are changing the number of photons. Changing the number of photons, but when we fix the frequency, means we use we use the same type of light. The first one is green, the second one also green color. Understand? Green. The energy of each photon still the same, but the second case is we fix the intensity, means we fix the number of photons, incident photons, but we change the frequency, means we change the type of light. One of it has less energy, each photon less energy, but the other, each photon has more energy. Okay? So this is what it changed. So the frequency is proportional to the energy of photon. Last time, the intensity is proportional to the number of photons. Okay? Now, the frequency is proportional to the energy of photon. One is the number of photons. Another one is about the energy of photon. So this one, now we are talking about energy of photon. So it's different from, this is about the quantum physics. This is about quantum, the quantum theory, quantum or the modern theory. If we are not talking about classical physics, is say the energy of the photon. Energy of photon depend on light intensity, which is wrong, which doesn't happen. This is the classical physics. But quantum physics, he say the energy of photon does not depend on intensity. Energy of photon depends on frequency, depends on the type of light instead of the intensity of light. It depends on the type of light. Blue light, red light. Okay, so energy of photon depend on the frequency. So we can say the higher the frequency, the higher the energy of each photon. The higher the frequency of light, the higher the energy of each photon. Like this one. Blue light has higher frequency, so it is like a bigger photon. Bigger photon carry more energy, right? So we can predict something like this. The higher the frequency, the energy of each incident photon is bigger, like a bigger photon. Okay, bigger photon. But the number of photons still the same because same intensity. Okay, number of photons still the same. So it's like higher frequency means it's a bigger packet of energy, bigger bundle of energy. Energy of incident photon higher. So kinetic energy of photoelectron ejected will be higher. Of course, it will eject more energetic electron. So you require a higher stopping potential to stop it. You imagine like a race car. A race car which maybe just a usual car. I travel very low speed, easy to stop. You need a low stopping potential. But if you go very fast like a racing car, very hard to stop. You need a higher stopping potential to stop it. That's a different the kinetic energy and the stopping potential, isn't it? That's why don't drive too fast. If you drive slowly, you press your brake just a little bit, you can stop your car. But you drive very fast, you need to brake very hard and very hard to stop your car. So you need a higher stopping voltage. Something like that. So it's the same thing like the analogy we made before. Okay, like this one. You look at this one. E equal to Kmax plus work function actually come from here. I interchange the formula, become this one. See? So let's say you have 100 ringgit. Maybe analogy like this. 100 ringgit. So now you have 100 ringgit. So your this is your Kmax. So you have remaining, after minus the ticket 50 ringgit, you still have remaining 50 ringgit kinetic energy, isn't it? But what if you have incident photon coming with 200 ringgit. Incident photon. This is maybe the 100 ringgit is maybe just the red light. It's just a red light, small energy. 100 ringgit. So the kinetic energy, this is the kinetic energy. This is the kinetic energy, 50 ringgit. The remaining energy after minus the work function, the binding energy. Well, now we use the violet, ultraviolet light, violet light, a bigger bundle of energy, bigger bundle. So the electron absorb a lot of energy from the photon. So minus the work function, you still have remaining 150 ringgit as kinetic energy. 150 ringgit as kinetic energy. So very energetic. The electron ejected, like if you have 50 ringgit kinetic energy, the electron ejected just very slow, the kinetic energy. But if you have the 150 ringgit kinetic energy, the kinetic energy very fast Kmax. Because the leftover energy a lot. There's a lot of leftover energy, isn't it? So we can say the higher, this is the E equal to HF. So the higher the frequency, the higher the energy of the higher the frequency of light, the higher the energy of each photon. So the higher the kinetic energy of each ejected electron. Because the electron absorb more photon energy, and that's why when it ejected, it got more kinetic energy. Harder to stop this electron. So we also know another formula, Kmax equal to EVS, isn't it? Kmax equal to EVS. So the higher the frequency, the higher the energy of each photon, the higher the kinetic energy of the electron ejected. So the higher the kinetic energy, the higher the stopping potential. You require a higher stopping potential to stop it. So let's look at the simulation here. I just want to show you this simulation. All right. Look at this one. All right, look at this one. I have different color. This is about frequency and wavelength. Okay, frequency and wavelength. Look at this one. Here I have a violet light, and also I have a orange light. Which one has this one has a smaller wavelength. Smaller wavelength, low wavelength means high frequency. This one is high frequency, and this one has a long wavelength. Long wavelength means low frequency. Okay, low frequency. Which one more energetic? Which light has more energetic? This one, high frequency. High frequency means this photon has higher energy. This one has low frequency. Low frequency is like orange light is just like red light. Low frequency. Low frequency means low energy. Let's look at the difference. This is the high energy, ultraviolet. Remember, ultraviolet. Violet is like ultraviolet. Ultraviolet is very energetic ray, like X-ray. Ultraviolet ray. It scorch our skin, isn't it? It scorch our skin. So ultraviolet, like violet, is very high energy, very high frequency. So electron ejected will be very energetic. Let's look at this simulation. See how fast the electron ejected? Very fast, very high velocity. Very high velocity, isn't it? Because this violet light has high frequency, and the photon is very big packet of energy. So the electron absorb a lot of energy, end up they have high kinetic energy. Okay, look at the orange light. Low frequency, small packet of energy, low energy also. Yeah, low frequency, small packet of energy, low energy, and the electron ejected also very less energetic. So velocity very low. Then look at this one. You see that it travels slower. Electron travel but going at a slower speed compared to just now. Yeah. This one you see move at slower speed, and you can see more electron. Actually, it's not actually more electron. The intensity is already fixed, 80%, 80%. But why you can see more electron? Actually, the electron ejected is still the same. It's just that because they travel very slow speed. When they travel very slow speed, so at almost all the time, they are still traveling. None of them have reached the anode yet. So that's why you can see more electron. But actually the electron ejected is the same for both because they have same intensity. Understand? It's just that because this one travel at a slower speed, so the first electron ejected not yet reached the anode, got another electron ejected out already because they all travel at a slow speed. The first or second electron ejected not yet reached the anode, then got another electron ejected already from behind. That's why they end up like clump together. They clump together, and they seems like a lot of electron. Okay. In short, what I can say, ultraviolet light, very energetic, high frequency, high energy, small wavelength, very small wavelength, high kinetic energy. It need a higher stopping potential. Okay. Whereas the orange light, very high, long wavelength, but very low frequency. When very low frequency, they travel small packet of energy, and each electron ejected with low kinetic energy. Low kinetic energy travel at slow speed and require lower stopping potential. Okay, that's it. You can see over here. Here you can see violet. Violet has 400 nanometer compared to the green 530 nanometer. Yellow is 580 nanometer, and orange light is 600 nanometer. So you can see the wavelength increases, isn't it? Wavelength increases. When wavelength increases, that means the frequency decreases. That means this one, the shortest wavelength means has very high frequency. Shortest wavelength means very high frequency. This one has the lowest frequency. Highest frequency, lowest frequency. Highest energy, lowest energy. You see, this one highest energy require higher stopping potential. You see, the stopping potential changes. You see, what changes is the stopping potential. This one require very high stopping potential. This one require very sorry. This one require very low stopping potential. Because why? Because ultraviolet light, the electron ejected very energetic. So it require very high stopping potential to stop it. But like yellow light, the electron ejected because the photon itself has a low energy, so electron ejected very less energetic. So it require slow stopping potential to stop it. But what is constant between all these is the current. You see, the current maintained at 80. The saturation current maintained at 80, 80, 80, 80. All of them have the same saturation current. Because why? Because I fixed the intensity. This one, intensity 60%, intensity 60%, intensity 60%, intensity 60%. Because when you have same intensity, it means they have same number of photons. So the electron ejected out is the same number of electron ejected. So all of them have the same current. You see here, the current here 41, 41, 41, 41, 41. All of them have the same photocurrent. Because they have same intensity. What changes is just the stopping potential. This one very highest stopping potential. This one lowest stopping potential. This one very low stopping potential. Because this ultraviolet light is very high energy. The electron ejected very high kinetic energy, require a very high stopping potential. The orange light or yellow light is just like the red light, very low energy, very low frequency, very low energy. So energy electron ejected very less energetic. Require a very low stopping potential. It just require a very low stopping potential to stop it. Okay. I think, but you see the red light. You see the red light has no current at all. But if we use a red light, just now we use yellow light and orange light, we still have the current flowing, 41, 41. But when you use a red light, no current at all. Why? Why is it like that? No saturation current at all. Why? This explains about quantum theory. It has a threshold wavelength, threshold frequency, or it has a certain threshold frequency. So not all light can eject electron. This explains back what I mentioned before about the phenomenon of photoelectric effect. Okay. Quantum physics says that the light must have a frequency greater than certain minimum value, threshold frequency, then only can eject the light. Then only can eject the electron. Only certain type of light can eject. Not all type of light can eject. So why the red light just now? Why the red light just now has no current at all? Because this wavelength is too high. Wavelength is too high, higher than the maximum threshold wavelength. Or we can say the frequency of this is lower than the minimum threshold frequency. This light has a frequency lower than the minimum threshold frequency required. Or we can say the energy of this incident light is lower than the work function. That's why no electron can be ejected out. So that's why no current at all, zero, no current at all is detected. Because this photon, this light, has not enough energy to eject the electron. Or we can say this is the case when this is the case. No electron is ejected because the photon does not have enough energy to eject the electron. Because it's just like you have 20 ringgit, not enough to pay for the ticket to enjoy the show, no entry. The energy of photon is less than the work function. The energy of photon less than the minimum energy required. The frequency is less than the threshold frequency. The wavelength is too high. Like what you see here, the wavelength is 700. Other people just how many? Other people just 400, 580, 530. Very short wavelength. This one has very long wavelength. Over the maximum threshold wavelength. Okay. See, the wavelength is too big already, too long, longer than the threshold wavelength. Okay. End up they have a very low frequency, lower than the threshold frequency. So that's why no electron is ejected, no photocurrent is detected by the galvanometer. Okay. So that's what I want to say. Okay. So let's move on to the next video. I will explain about this graph. Okay. About this graph. So the next video, sorry, where is it? Yeah, about here, this graph. Okay. Maybe I just explain, yeah, straight away. All right. So you can see here, high frequency. You need high frequency of light. You need a higher stopping potential. That's it. So we can look at this one. This one, you see that higher frequency of light. You see these two diagram. Actually, it's the same thing. I have shown over here. This one, okay. You see this one. So this one actually, this graph actually represent the graph I shown here. You see, like the violet light is very energetic, very high frequency, need a high stopping potential. The orange light, very low frequency, low stopping potential. So like this one lah. You see this graph. Okay. See this one. The frequency 2 is higher than frequency 1. Frequency 2 higher than frequency 1 means the VS2 will be bigger than VS1. Means the second light has need a higher stopping potential than the first light. Yeah, VS2 stopping potential for wave 2 is bigger than the stopping potential for wave 1. Okay, so don't regard about the negative sign. Negative sign is just about the reverse voltage. Okay, we are only talking about the value, only about the value, only about the modulus, Vs2 is the value of it, the magnitude of it is bigger than the magnitude of Vs1. So normally we can say something like maybe we just give a value. This one Vs2 is negative, maybe negative 20 volt. This Vs1 is maybe negative 10. So it's still in terms of the magnitude. Okay, the 20 volt is bigger than the 10 volt. Okay, the negative sign is just about the reverse. Reverse voltage. The negative sign just means about the reverse voltage. It does not affect the value. Yeah, we are just talking about 20 volt and 10 volt. That's it. Just ignore the negative sign. So the Vs2 is bigger than Vs1. So we can say the frequency 2 is bigger than frequency 1. So maybe the frequency 2 is a violet light. Maybe this one is ultraviolet light. This one frequency 1 maybe is orange light. Orange light. Yeah, orange light maybe lah. So violet light has higher frequency, need a higher stopping potential. Orange light, low frequency, need a low stopping potential. Okay. Look at this one. Look at this graph, and we have another graph here to check. So according to this E equal to Kmax plus work function, okay, we rearrange the formula. Work function go to the other side. So Kmax is actually the remaining energy. It's actually the remaining energy. Yeah, isn't it? It's the remaining energy after the energy of the photon minus overcome the work function. After the photon overcome the work function, that's the remaining energy you have on the electron ejected. Okay, so Kmax is the energy of photon minus the work function minus the binding energy. That's the remaining energy on the electron. So energy of photon is HF. So we can see from here also, the higher the energy of the higher the frequency of the photon, more energy of the photon, more kinetic energy. Higher kinetic energy, higher remaining kinetic energy on the electron. Okay. So that's why from this one, Kmax equal to HF minus work function. Kmax become the y-axis, F become the x-axis, and then just apply y equal to mx plus c. Yeah, this one makes another linear graph. You see that? Kmax is the y-axis, F is the x-axis, frequency is the x-axis, and h is the gradient of the graph. Yeah, you know the gradient of this graph is h. And then the y-intercept become the c. The intercept is negative w naught. Okay. So you can see the higher from here also, you can see the higher the frequency, the higher the kinetic energy. The higher the frequency of the photon, the higher the kinetic energy of the ejected electron. So okay, why? Okay, now you know the y-intercept is w naught. How about the x-intercept? Why the x-intercept is f naught? Let me prove to you. Okay, so maybe this one we just substitute. If we want to find the y-intercept, means we substitute the x with 0. That means we substitute f with 0. Okay, let's substitute. So Kmax equal to hf minus work function. So now we want to find the y-intercept. We substitute the f with equal to 0. Because our y-intercept is when f equal to 0. Okay, when f is equal to 0. So substitute f equal to 0. So what do we have? Substitute f equal to 0. So Kmax equal to negative w naught. Because the HF gone already. Because f equal to 0, isn't it? So Kmax equal to w naught. So in the end, what do we get? We substitute w naught with hf naught. Because Okay. Sorry. I shouldn't. No. I actually shouldn't substitute the f with 0. If I substitute f with 0 means I find the this one is to find the y. This one is to find the y-intercept. Okay, I wrongly. Yeah. This one is the y-intercept. If I substitute f with 0, if I substitute f with 0, that means I got the y-intercept. You see, this is the y-intercept. This is the y-intercept. So Kmax equal to negative W naught, isn't it? Now, if I want to find the x-intercept, that means I need to substitute the k equal to 0. It should be k equal to 0. Now, what if I substitute k equal to 0? The Kmax, the Kmax I substitute equal to 0. So what do I get? So now, okay, I substitute Kmax equal to 0. Now I substitute this one equal to 0. So what do I get? So 0 equal to HF minus work function. Okay, HF minus work function. So HF is equal to work function lah, isn't it? Now work function I substitute with what? I substitute with HF naught. W naught I substitute with HF naught. So I cancel the H. Now I got F equal to F naught. So when Kmax equal to 0, so my frequency is the threshold frequency. This is the threshold frequency. Okay, so the x-intercept is the threshold frequency. The y-intercept is the work function, negative W naught. Okay. Now, how about this one? Now I substitute. So I got this graph. Now I substitute this Kmax with E equal to Vs. Okay. Electron times stopping potential. I substitute into that, and then this E and then I divide both sides with E. I divide the left hand side and right hand side with E. So I end up with this formula. Okay. The y-axis now is stopping potential. Okay, y-axis stopping potential, and the x-axis now is also frequency. So my gradient now, my gradient is h over E. Last time is h, now is h over E, and then my y-intercept is negative W naught over E. This is my y-intercept, that negative W naught over E. Okay. So the x-intercept also F naught. If you do the same thing again, you substitute the stopping potential Vs. Okay. If you do the same thing again, Vs you substitute equal to 0, and then you will still find the frequency is the threshold frequency. Okay. So from this equation also we can see the higher the incident frequency, you need a higher stopping potential to stop the ejected electron, because the ejected electron has high kinetic energy. You need a high stopping potential to stop it. Okay. So that's it for so higher frequency need higher stopping potential. Okay. So this two graph is important. It's important because you must know for this graph, the x-intercept is the threshold. The x-intercept is the F naught, threshold frequency, and then the y-intercept depends. If Kmax is W naught, negative W naught, if Vs is negative W naught over E. This is very important graph. You must know this what they refer. You must know what is the x-intercept and also what is the y-intercept, because the question will ask you the value. What is this represented? Sometimes the axis also will interchange. The Vs will interchange with F. It become the graph like this. It will become the graph something like this. Also, then this one become F. This one become Vs. So what do you think? If they interchange, how? Interchange. Then you must know what it represents. Then this one is the F naught already, and this one is the it actually become the graph something like this. So this one become the W naught over E. Understand? You must know the interchange. You can interchange also. Understand? So okay. So I just want to conclude that intensity just change the current. Intensity just change the current. The higher the intensity, but it means more number of photons, more current. So you can see the stopping potential is fixed, but the saturation current will increase. It just changes the saturation current. Okay, intensity just change the current, but for frequency, intensity just change the saturation current, but stopping potential is fixed. But for the frequency, it will change the stopping potential. It's change the voltage. It change the voltage, but the current is constant. The current is constant. Only the voltage changes. Yeah. This one change current. Intensity change current. Intensity change current. But the frequency change voltage. That's all for this video. Okay. Welcome to the last one.